Hi, my name is Owen Welsh, and I did my project on searches for gamma-ray bursts with multi-messenger detections. So, some background information before I start. Gamma rays are highly energetic bursts of electromagnetic energy coming from high-intensity cosmic events. They have a main emission of gamma rays that last from seconds to hours, and then a much longer afterglow of photons at lower energies. Neutrinos are elementary particles with very low mass, that are unaffected by strong electromagnetic forces. In other words, they barely interact with ordinary matter, and although they are everywhere, they were very difficult for humans to detect until recently. Gravitational waves are fluctuations in space-time caused by compact objects such as neutron stars and black holes. Astronomy research beyond our solar system is based mostly on inferences, since we can rarely observe our objects of study directly. Finding a multi-messenger event, a singular event we can detect multiple different messengers from, would signify either a hypernova, which occurs when a star more than 30 times the mass of our Sun collapses to form a rotating black hole, or a kilonova. The result occurs when a binary system of two neutron stars or a neutron star and a black hole merge into one object. I've added these pictures to better explain the difference between the two. On the left is a depiction of a hypernova, essentially just a very large supernova. In fact, the line between the two is blurry sometimes. On the right is a kilonova, this one a merger event between a binary neutron star system. This event is rarer, as neutron stars require stars in a specific range of masses, and a binary system including one, along with another high-density object, is very rare. Both events produce gamma-ray bursts, but different kinds. Hypernovas produce long-duration gamma-ray bursts, which last anywhere from 2 seconds to 10,000 seconds. Kilonovas, on the other hand, produce primarily short-duration gamma-ray bursts, which last from mere milliseconds to 2 seconds, although they have been detected to produce long gamma-ray bursts as well. Both events also produce gravitational waves and cosmic neutrinos. As such, a multi-messenger event could come from either, and only once the event is actually detected can it be determined which one of the two was actually the source. For my project this summer, I was looking for evidence of multi-messenger events by looking for overlapping detections of gamma-ray bursts, high-energy neutrinos, and gravitational waves. The hypothesis was that said event would be either a hypernova or a kilonova. The objective was to analyze various data sets to look for overlaps that would indicate different detections were from the same multi-messenger event. For neutrinos, I looked at the Ice Cube Neutrino Observatory in Antarctica, with the public data release of muon neutrino detections from 2008 to 2022. Gamma-ray burst data came from the Swift Gamma-ray Burst Explorer, which contains data from 2004 to 2026. Gravitational waves data came from the Laser Interferometer Gravitational Wave Observatory, or LIGO, with data from 2015 to 2025. The only software used to compare the data sets was Excel spreadsheets. To start, I standardized the units across all data sets using modified Julian date for time and degrees for the position in the sky. The gamma-ray bursts were used as the standard to compare the time of other data sets to. The valid time period started at the moment the GRB was first detected, and ended after that time, plus the T90. Which is how long it took for 90% of the gamma-ray burst to pass the detectors, and the error of that T90. Both Ice Cube and LIGO only have one detection time, so I checked if these times fit within any of the Swift time windows. With LIGO, Doing this comparison for the years 2016 to 2022 produced 0 valid events. Thus there was nothing else to check. With IceCube, 64 events within the same 7 years were confirmed to be temporally coincident, meaning their times of detections overlapped. For those 64 neutrino detections, the next step was to check if they were spatially coincident, or if the position in the sky they originated from overlapped. For both data sets, I was looking at their right ascension and declination for their position, and then used their angular error to create a circle of uncertainty around these points. If there were any event whose error circles overlapped as on the right, they would be spatially coincident. However, there were no such events in the data set, and all checks looked like the image on the left. At the end of the internship, no overlap was found between any of the data sets, indicating that there were no multi-messenger events represented between these specific data sets. 64 Swift and IceCube events were temporally coincident, but none were spatially coincident as well. The same GRB's events were then compared with gravitational waves from LIGO, but none coincided. In conclusion, I was looking for multi-messenger events. Unfortunately, we did not find any using these methods. This does not indicate they are not present, but that the specific data sets used did not contain them. No multi-messenger events are represented between Swift GRBs and either IceCube neutrinos or LIGO detected gravitational waves from 2016 to 2020. There are 8 years remaining that one could look at between IceCube and Swift, and 3 years between Swift and LIGO. In the future, one could develop code to allow this analysis to happen more automatically, which would allow for much faster analysis of further data. Thanks to my mentor Mike, Ariana and Lynn, and the rest of the N3 program, and I'll now open the floor to questions.